One large class of functions that we haven't really thought about yet is rational functions. We can integrate polynomials, so shouldn't we be able to integrate ratios of polynomials, which is what rational functions are? We do have some tricks that can work for some rational functions, so here are a few examples. For example, the integral of 1 over 3x minus 1, this is sort of a clear case for using a u substitution. We can do u equals 3x minus 1, and then du is 3dx. That means 1/3 du is dx. And then we can do our substitution, so we get integral of 1 over u, 1/3 du. We can move that 1/3 outside. Integral of 1 over u is natural log absolute value of u plus a constant, and then undo the substitution. 1/3 natural log absolute value 3x minus 1 plus a constant. Okay, so if our denominator is pretty simple, then we already have some tools to integrate rational functions. Let's look at another example. So how about 1 over x squared plus 2x plus 1? Anytime you're working with a rational function, it should occur to you at least some of the times that maybe factoring would be a good idea, because a rational function is a ratio of polynomials, so you could always factor the polynomials and hope that something nice happens. In this particular example, this does factor this denominator, so we get 1 over. So if you look at this carefully, what you get when you factor this is x plus 1 squared dx. And right, this looks essentially like 1 over a variable squared, which is something we can integrate using a power rule. So again, if we do a little u substitution, you might not need to write this one out to figure out this u substitution, but if we take u to be x plus 1 and du is dx, then this becomes integral of 1 over u squared du. And taking an antiderivative, we get minus 1 over u plus a constant, and then undo the u substitution, minus 1 over x plus 1 plus a constant. Okay, so powers, this is essentially an example of powers of the variable in the denominator. So we can integrate powers of variables in the denominator. What else do we already have tools to deal with? Well, there's one sort of special rational function that we have an antiderivative for straight away, and that's 1 over x squared plus 1. This one we just know. It's inverse tangent, plus a constant, of course. So, all right, the sum of squares in the denominator we have an antiderivative for immediately. One more example, integral of 1 over x squared plus 2x plus 2. Now this one doesn't factor so nicely, but one thing that we can do is complete the square. Anytime you have a quadratic, completing the square is an option. Sometimes it doesn't really help the situation, but in this example, if we complete the square in the denominator, so since our leading coefficient is 1, we take this linear coefficient, 2, we divide that by 2, which gives us 1, we square that, that gives us 1. So the missing part of our square is 1, so x squared plus 2x, so plus 1. Now this is going to be our perfect square. Now we need to make up the plus 2 that we started with, so we need another plus 1 dx. Okay, now this is integral of 1 over x plus 1 squared plus 1 dx. And now we could do a u substitution again. If we take u to be x plus 1, du is dx. We get integral of 1 over u squared plus 1 du. And this is going to give us an arctangent again. So inverse tangent of u, but u is x plus 1. plus a constant. So here we were able to complete the square, and that let us make a u substitution to figure out the antiderivative. One final example that we should look at is what happens if the degree of our numerator is larger than the degree of our denominator. So if you look at all those previous examples, the degree of the numerator was 0 on all of them. But what happens if we have a polynomial in our numerator that's actually of larger degree than the polynomial in our denominator? This is sort of the rational function form of an improper fraction where the numerator is bigger than the denominator. And the tricks that we saw a minute ago really only work if the numerator has a degree smaller than the denominator. So we need to figure out some way of making that happen here. And the way to make that happen is just to do long division. So we have x squared plus 3x minus 4, and we're dividing this by 2x minus 1. So remember how polynomial division works. We need some part of a quotient here that when you multiply it by the divisor, you get x squared. So that would be 1/2 x. Now 1/2 x times the divisor gives us x squared minus 1/2 x. Then we subtract. The x squareds cancel. The whole point of choosing 1/2 x up here is that the highest degree term here should cancel, which it did, so that means we did something right. And then 3x minus negative 1/2 x, that's 3x plus 1/2 x, that's 7/2 x, and minus 4. And now we need to choose something up here so that this 7/2 x is going to cancel, and I think we're going to need plus 7/4. So 7/4 times 2x is 7/2 times x, and then 7/4 times minus 1 is minus 1. Sorry, minus 7/4. Subtract. The high degree term cancels, that's good. And then minus 4 plus 7/4 is going to be 9/4, I think. Okay, so what this quotient is telling us is that this integrand that we started with is equal to, now we haven't integrated it yet, so we're just algebraically rewriting the integrand. The integrand is equal to the quotient, which is 1/2 x plus 7/4, and then plus the remainder over the divisor. So plus the remainder, 9/4, times 1 over the divisor, 2x minus 1 dx. Okay, now notice the result of this long division is a polynomial piece that was the quotient plus a rational piece. The rational piece still has the same denominator as we started with, but now the numerator has degree lower than the denominator. And that means that we can use the tricks that we saw before. This one in particular, we can integrate just by doing a little u substitution. So integrating 1/2 x gives us 1/4x squared plus integral of 7/4 is 7/4x plus, let's move this 9/4 outside of the integral, integral of 1/2x minus 1 dx. So 1/4x squared plus 7/4x plus 9/4. And then you may need to do a little u substitution to figure out this antiderivative. The u substitution is going to spit out a factor of 1/2, so. And then we're going to get a natural log absolute value, 2x minus 1. And then we should simplify these fractions. 9/4 times 1/2 is 9/8. Okay, so if we start with a rational function whose numerator has degree larger than its denominator, all we need to do is polynomial division to turn it into a polynomial plus a rational function whose numerator has low degree. And then we can use our previous tricks to figure out the antiderivative.